Welcome to the Explainer. Today, we're opening up the playbook on one of the most elegant patterns in all of programming. Seriously, it's like a single key that can unlock some of the absolute trickiest problems you'll ever face. So let's jump right in.
So, have you ever just stopped and wondered how a computer solves a Sudoku puzzle faster than you can even think about it? Or how it can find its way through a super complex maze? No problem. It really feels like magic, right? But it's not. It's all about having the right strategy.
You see, at its core, the computer is just trying out every single possible path. But it does it in this incredibly clever and systematic way. It never gets lost. It never forgets where it's been. And this universal strategy, it's called recursion.
To make this feel a bit more real, let's connect it to something you might have seen before, like the merge sort algorithm. Remember that? It sorts a big list by splitting it in half, sorting those halves, and then merging them. But how does it sort the halves? Well, by splitting them in half. It just keeps breaking the problem down and down until it's completely trivial. You know, like sorting a list with only one thing in it. That is the recursive mindset. Just solve one tiny piece and then trust the process to do that over and over again.
Okay, so let's dive into the first and most fundamental pattern in our whole playbook. This is the bedrock. Everything else is going to be built on top of this. It's the simple logic of making a choice. Let's imagine a classic problem, subset sum. We've got a list of numbers, and we need to find all the different groups of those numbers that add up to a target. For every single number on that list, you have two and only two choices. You can pick it and add it to your total, or you can not pick it and just move on. That's it.
And this simple process, it creates a kind of decision tree. We'll start at the very first number, we pick it, and then we recursively explore that entire path to see where it goes. Once that whole path is finished, we pop back up to the start and we explore the other choice, not picking that first number. By doing this for every element, we systematically explore every single combination there is.
So by making this simple pick or not pick choice for each of our n elements, we end up exploring 2 to the power of n possibilities. It's a brute force approach, for sure, but this simple pattern guarantees that we check every single possible subsequence. Literally, no stone is left unturned.
All right, so that pick, not pick thing is perfect for finding groups of things, like subsets. But what happens when the order of the elements actually matters? This brings us to our next pattern, which is all about handling permutations. And this is where our thinking has to evolve a little bit.
So one way to generate all the arrangements, or permutations, is to use extra memory, right? You could use a map or a set to keep track of which elements you've already used. But there's a much more elegant way to do it. Instead of using up extra space, we can just swap elements around within the original array to create new arrangements. And the key to making this work is a really powerful idea called backtrack.
And there it is. This right here is the big aha moment of this whole explainer. To explore all the different arrangements, you swap an element into place, you go explore all the possibilities from there. And then, when you come back from that exploration, you swap it back. You undo your choice. And that undoing part? Well, that's the whole essence of backtracking.
So the whole thing boils down to this really beautiful three-step dance. First, you swap. You make a choice. You're saying, let's see what happens if this element is first. Second, you recurse. You dive down that rabbit hole to see where that choice leads. And third, and this is the magic part, you swap it back. You undo the choice. You're basically just cleaning up after yourself, leaving the array exactly how you found it, ready for the next path to be explored.
Okay, now we get to see the real, raw power of this choose, explore, unchoose pattern. This one simple idea is pretty much the skeleton key that unlocks solutions to some of the most famous and famously difficult puzzles in all of computer science.
Think about it. The N-Queen's puzzle, building a Sudoku solver, finding a path for a rat in a maze, even something like splitting a string into palindromes. On the surface, they all look wildly different. But underneath it all, they're running on the exact same engine. You make a choice, you see what happens, and you backtrack if it turns out to be a dead end.
Let's try and make this super tangible. Look at this Sudoku board. How would our pattern actually work here?
It's the same dance, just with different steps. First, we find an empty cell.
That's our decision point. Then we choose. We try placing the number 1 in that cell. We check, is that a valid move? If it is, great. We explore by recursively calling our solver on the rest of the board. But what if that path fails? Well, then we unchoose. We backtrack. We erase the 1 and we try a 2 instead. And we just keep doing that until we find a number that actually leads to a full solution.
This quote from our source material about the n-queens problem just says it all so perfectly. The choice is placing a queen on the board. The exploration is trying to solve for the rest of the queens. And the backtracking, well, that's removing that same queen so you can try putting her in a different spot. You have to clean up your own mess before you can try something new.
So up until now, we've been talking about finding all the possible solutions. But what if you only need one? I mean, with Sudoku, you just need one valid board, right? We can make a really simple but incredibly powerful tweak to our pattern for a massive optimization.
See, to find all solutions, we just let the recursion run wild and explore every single path. But to find just one, we change our function so it returns a Boolean, a true or false. The moment a recursive call stumbles upon a valid solution, it immediately returns true. And that true value just bubbles all the way back up the call stack, telling every previous step, hey, stop what you're doing, we found one, we're done.
And this simple change is just so incredibly powerful. It prunes the search tree like crazy. As soon as that one valid path is found, we stop exploring all the other millions, maybe billions of potential branches. It saves just a massive amount of pointless computation.
So as we start to wrap this up, I hope it's becoming clear that this is so much more than just a neat coding trick. It's really a fundamental way of thinking about and breaking down problems. We've kind of built this whole thing up, right? We started with a simple pick, not pick choice. Then we leveled up to the powerful choose, explore, unchoose backtracking pattern that can solve these incredibly complex puzzles. And all of it, every single bit, rests on that one fundamental recursive idea. Break a big, scary problem into smaller, identical, manageable pieces.
And honestly, this is the leap of faith you have to take with recursion. You don't need to wrap your head around the whole complex problem all at once. Your only job is to define the rules for one single step. How do you make one choice, explore it, and then undo it? If you can figure that out, you can just trust the beautiful, cascading power of recursion to handle everything else.
I absolutely love this quote from one of our sources because it just drives home how universal this pattern is. Once you really see this structure, this recursive backtracking pattern, you're going to start seeing it everywhere. It's a tool you will want to keep in your problem-solving toolkit forever. I repeat, forever.
And that kind of leaves us with a final, lingering thought. Forget puzzles for a second. What other huge problems, maybe in logistics or AI or even science, could be cracked open with this simple little dance of choosing, exploring, and backtracking? Thanks for joining us on The Explainer.